The device you're using to watch this video contains a marvel of human engineering, a central processing unit, or CPU. This tiny silicon chip, often smaller than your fingernail, performs billions of calculations every second, forming the beating heart of our digital world. At its core, a CPU is a complex integrated circuit designed to execute instructions. These instructions, written in binary code, allow the CPU to perform arithmetic, logic, control, and input-output operations that drive everything from simple calculators to sophisticated artificial intelligence systems. The foundation of modern CPUs lies in transistors, microscopic electronic switches that control the flow of electrical current. Modern processors contain billions of these transistors, each measuring just nanometers across. These transistors are arranged into logic gates that perform basic operations like AND, OR, and NOT, which form the building blocks of all computer operations. The CPU operates through a continuous cycle known as the fetch-decode-execute cycle. First, it fetches an instruction from memory. Then it decodes this instruction to determine what operation needs to be performed. Finally, it executes the instruction, manipulating data or controlling other parts of the computer system. This cycle repeats billions of times per second, creating the illusion of simultaneous operation. Inside every CPU are several critical components. The arithmetic logic unit performs mathematical calculations and logical operations. The control unit coordinates the activities of all CPU components. Registers provide ultra-fast temporary storage for data being processed. The cache memory stores frequently accessed data to reduce the time spent waiting for information from the slower main memory. Modern CPUs have evolved dramatically from their early predecessors. Most now feature multiple processing cores, effectively placing several CPUs on a single chip. This allows for parallel processing, where different tasks can be handled simultaneously. Advanced features like pipelined architecture allow CPUs to begin processing a new instruction before completing the previous one, significantly increasing efficiency. The manufacturing of CPUs involves some of the most precise engineering processes humans have ever developed. Creating these chips requires clean rooms thousands of times cleaner than hospital operating rooms. The photolithography process uses ultraviolet light to etch circuits onto silicon wafers with features measuring just a few nanometers, so small that quantum effects must be considered in their design. Clock speed measured in gigahertz determines how many cycles a CPU can perform per second. However, raw clock speed is just one factor in overall performance. The instruction set architecture, cache size, number of cores, and thermal efficiency all play crucial roles in determining a processor's capabilities. Energy efficiency has become increasingly important in CPU design. As transistors have shrunk, power leakage has become a significant challenge. Engineers have developed sophisticated power management techniques, including dynamic frequency scaling and selective core activation, to balance performance with energy consumption. The evolution of CPUs represents one of humanity's most remarkable technological achievements. From the first microprocessors containing thousands of transistors to today's chips with billions, these devices have transformed every aspect of modern life. They enable the smartphones in our pockets, the servers powering the internet, the supercomputers modeling climate change, and countless other technologies that define our digital age. As we continue to push the boundaries of physics and engineering, CPUs will evolve further, enabling new applications we can barely imagine today. The principles that govern their operation remain a testament to human ingenuity and our ability to harness the fundamental properties of matter to create tools of extraordinary complexity and capability.